Okay. Binomial means what? Two possible outcomes. Yes.
Double.
This is what really happens. It could be on, off, it could be good, bad, right, wrong, pass, fail. These are, you can calculate probabilities on events that only have two possible outcomes. Flipping a coin, yeah. There's going to be head or tails, yeah. So in the first part, we're going to talk about the basics. Of binomial probability distributions. So a definition. Binomial probability distribution is when a procedure meets or satisfies the following requirements. So binomial probability distribution is a procedure that satisfies the following requirements. One, the procedure has a fixed number of trials. By trial, we're talking about each event. You roll each time you roll a die, each time you flip a switch. So it's finite, it's countable. Each event or trial is independent. Independent, we talked about yesterday. It doesn't, each event does not affect the outcome of the next event. Let's use trial. Each trial or event has only two possible outcomes. And each trial has the same probability. So it has to be a finite number of tries, yes, because it can't go on forever. Each trial is independent. In other words, they don't affect each other. There are only two possible outcomes, and each event has the same probability of occurring. So what we're looking for here is the probability where you're going to use success or failure. The probability of success, we'll call it little p. And the probability of failure is Q. That's the probability of failure or not succeeding. Another way you could write that is the probability of the event not occurring. You could also do that. The formula for Q is 1 minus P. So the probability of failure is 1 minus the probability of success. Conversely, P is the same thing as 1 minus Q. Little p is 1 minus Q. Because if you think about it, the probability of success and the probability of failure has to equal what? 1. N is the number of trials or events. X is the outcomes of each event. So now we're going to be we're sticking to these because little p represents the probability of success. Q is a probability of failure. Let's look at example 1. When an adult smartphone owner is randomly selected with replacement, why is that important? Right, so the denominator never changes because remember, each event, each time you try this, it has to be the same. So if you try this, if you pick a person from at random and you ask them, what kind of do you have a smartphone? You have to put them back in. So the next event has the same chance of being occurring. Can you pick the same person more than once? Yes, because it's randomly selected. So when an adult smartphone owner is randomly selected with replacement, there is a 0.05 probability that that person is cashless, never carries cash. So cashless. We want to find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. So this is going to be our success. That's going to be our little p. And then we're going to ask, does this procedure result in a binomial distribution? If this procedure does not result in a binomial distribution, identify the values of n, x, p, and q. So how many n's are we going to have? What's n going to be? 10. We're going to try 10 people. Remember, I said we want to find the probability that among 10 randomly selected adults, exactly 2 of them are cashless. So n is 10, x is going to be 2. What's p going to be? Zero 0.05, and that makes q 1 minus p, which is 1 minus 0.05, which makes it 0.95. So is this a binomial distribution? Remember, it has 4 conditions. Is there a fixed number of trials? 10. Are each event independent? Yes. Are there only 2 possibilities of outcomes? The person either has money or no money. Each trial is the same probability. Yep. So it is a binomial distribution. Correct. Because it has to follow the 4 requirements. And then we labeled N, X, P, and Q. %5 guideline. for cumbersome calculations. What this thing says is when sampling without replacement, and the sample size is no more than 5% of the size of the population, then treat the selection of samples as being independent. Why is that important? Why do you have to treat it as if they're independent? Right. Because we don't want one event to influence another. So we're just going to avoid it. Here's the formula we're looking at. The formula for the binomial probability. Each event, probability of X, is equal to n factorial over n minus X, because n is population, as size, over X factorial, times the P of X times Q of n minus X. We've defined what N, P, Q, and X are already. P was what? Probability of success. Q is, and look at these two by themselves. Remember, if we have N total samples, let's say it's 10, and we chose X is 2, we only want 2 out of the 10. So here in our formula, we have P to the power of X. That's P to the power of 2. How many do we have left out of the 10? Which is, those have to be the failures. That's why it's Q to the power N minus X. So the powers of P and Q, if you add them together, has to be how many samples you have. Because that looks at all the possibilities that we have. The probability is success and everything else is failure. Now, what we're looking at, this first part here, that is what's called a counting method of determining the permutations or combinations possible. Combinations possible. It's denoted as NC of X. N is a total number of samples that you have. That goes on top as a factorial. On the bottom, it's N minus X factorial times X factorial. What it does, it's always going to give you an integer. It's never going to be a decimal. So what is a factorial? The exclamation mark is a factorial. What it tells us is multiply everything from that number down to 1. So 3 factorial is 3 times 2 times 1. which is 6. 5 factorial would be 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 6 is 120. So that's what a combination is. It's always going to be an integer. It tells us how many ways can we arrange it. And then again, from that formula, we know what x is, we know what n is, and that gives us our exponents for a pass and fail part. Okay, so let's look at this. Unfortunately, these will require using either Excel, a calculator, or one of the programs that this course uses. But I'll show you an example of this. Let's define P of X as the probability of success is 0.6. So if P is 0.6, what's Q? 0.4, because together they have to equal 1.0. And we have a total of 10 elements. We want to know how many, we want to know exactly 4 elements. So X is 4, N is 10, P is 0.6, and Q is 0.4. So we want to know what's the probability of exactly 4 being correct. So what we have to do first, we have our formula. It's going to be the NC of X. It's a combination formula, that n factorial over n minus x factorial times p to the power x, q to the power n minus x. So n factorial would be 10 factorial divided by 10 minus 4 factorial on the bottom times 4 factorial. Times the probability of success is 0.6. And we want 4 of those. So it's 0.6 to the power 4 and 0.4 to the power 10 minus 4. So the probability of 4 being correct. So on top, we have 10 factorial, which is 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. On the bottom, we have 10 minus 4, which is 6. 6 factorial is 6, 5, 4, 3, 2, 1. Times 4 factorial, which is 4, 3, 2, 1. It's not as hard as it sounds, because once you look at this, the n minus 10 is 6 factorial. So we can cancel 6 down to 1 from top and bottom. So the 6 factorial cancels on top and bottom. So all we have left on top is 10 times 9 times 8 times 7. On the bottom, we have 4 times 3 times 2. Of course, times 0.6 to the power 4, 0.4 to the power 6. We know 4 times 2 is 8. That cancels with the 8 on top. The 3 cancels with the 3 and the 9. So we have 10 times 3 times 7. So that combination, everything cancels out. that we can't, because remember, we used to have 10 times 9 times 8 times 7 over 4, 3, 2. The 4 times 2 on the bottom equals the 8 on top, so they cancel. The 9 on top cancels with the 3 on the bottom. So all we have left is 10 times 3 times 7. 3 times 7 is 21 times 10 is 210. Times 0.6 to the 4th times 0.4 to the 6th. Calculate all those, and there's your answer, the probability of getting exactly 4. Now, here's another question I'm going to ask of y'all. What the same information, the probability of success is 0.6, the probability of failure is 0.4, n is 10, x is going to change. So what if now I want, what is the probability of getting less than 3? With the same information, probability of getting less than 3. What does that entail? Well, what's less than 3? That means the probability of 2 plus the probability of 1 plus the probability of 0 happening. So we have to look at all of those that satisfy those conditions. If I say less than 3, then I have to find all the probabilities of anything less than 3. 2, 1, 0. Or if I said greater than 7, it'd be 8, 9, and 10. So what I got to do, I have to do those calculations for each one of these and then add the final answers together, which will take time. Example 4. Oh, also remember, if your probability, if we do those, if your probability is something like 0.000000859, since we have a lot of point zeros there, your answer is going to be 0 positive. Yeah, because that number is a positive number. It's not negative. It's 0.00. But since it's so small, it's very close to 0. So the way you'd answer it online would be 0 with a plus sign behind it. Okay, let's look at example 4. Then that's the last one we have. Yes. No, we have one more section in chapter 5. No, we have one more example to do. Yeah, then we'll do example section 3 tomorrow. And then we'll start chapter 6 also. Example 4, veggies. The Gallup poll says that 5% of US adults are vegetarians. If randomly selected 5 adults, find the following probabilities: that exactly 2 of the 5 are vegetarians, then the probability that there are fewer than 3 vegetarians. So we have to figure out N, X, P, and Q. So what's my N? How many adults am I looking at? 5. So N is 5. So what I want to look at the first one, what is the probability of exactly 2? So X is 2. Probability of success is, it says 5% of US adults are vegetarians. So success would be 5%, which is what in decimal? 0.05, which means what's failure? 95%, 0.95. So the probability of exactly 2 would be 5 factorial divided by 5 minus 2 factorial times 2 factorial, 0.05 to the power 2, 0.95 to the power 3, which is n minus 2. And work those out, you get your probability. 5, 4, 3, 2, 1. 3, 2, 1, 2, 1. Five. So 3, 2, 1 can cancel. And then the 2 on the bottom can cancel with the 4 on top. So we have 5 times 2 is 10 times 0.05 squared, 0.95 cubed. Remember, the exponents have to equal n. So that's the first one. The next one says fewer than 3 vegetarians. So x is less than 3. If x is less than 3, then it's going to be 0, 1, and 2. So these are my x's that I have to redo all these calculations over with. And let me see. The last topic, because remember, we deal with distributions. It's a binomial distribution, which means we have to be able to find mean, variance, and deviation. Binomial distribution, to find the mean, the variance, and deviation. So it's mu equals n times p. That tells us the mean. The Greek mu is the population mean. It's the multiplication of n. What's n represent? The total number of elements that you're testing, your sample size. And p is probability of success. Multiply those together, and that's your mean, n times p. The variance is rho squared. That's n times p times q. So your probability of success times your probability of failure times n, and that's it. And your deviation is simply the square root of n times p times q. And the significance rules are exactly the same. It's mean plus or minus 2 standard deviations. Significantly high, significantly low, not significant. And that's all of them. That's it for that section. What do y'all think? Yeah, binomial distributions, once you look at it, it's only got 2 numbers. It's either pass or fail. You had a question in there? All right, so tomorrow we'll do section 3. We'll answer questions first, and then we'll do section